Okay, so this is CS 3500. So those of you are new majors, so congratulations on being new majors. I'm having a little bit of audio-visual problems, so I'm going to have to type and watch to see if I can fix it here. Does anyone, who needs an ad code? So there are a handful of people that need an ad code, presumably because you were just admitted and whatever. So see me after class about that. I'll try to help you. Let's see if I can get this to project. Now this is, I've tried two ways to get the projector to work. It's aggravating.
Well, you used to do other things. What's that, Joseph?
Okay, I guess I'm going to have to work without a projector. The slides are all on the Canvas page if you have a laptop and want to look, or they'll be there next time. So I want to talk first about how the class will operate. So sort of just the mechanical aspects of what you expect week to week in the class. So first of all, the course has as prerequisites 1410 and 2420. So what's important is that you know how to program and that you understand some basic algorithms and data structures. So that's why we have those as prerequisites. So what we'll be doing in this class is studying software engineering. Now, software engineering is a big field, and in particular what we're going to be looking at is, I would call more like personal software engineering. Software engineering as it applies when you work by yourself or in a group of two, in a pair. So why is software engineering something you have to study? What is software engineering? Who has an idea? How's it different from programming? Yeah?
Software engineering involves collaboration and organization.
Okay, so it involves collaboration and organization. Okay. Any other takes? Yeah?
Programming is more like building the brains that run it, and software engineering is making like the whole body run.
Okay, I said programming is like building the brains and software engineering is making the whole body run. Okay. Yeah?
I think the software engineering is like all the stuff you do beforehand and afterward, right? Like all the stuff like the planning that gets put into it, not just the code, but the programming is just the code.
So he says it involves not just the code, but planning and other things that it takes to get a program written. Any other ideas? Yeah?
A lot more API design.
A lot more what design?
API design.
API design? Okay. Okay. The basic idea is that as programs when programs are small, when you're writing small programs like you have for 1410 and 2420, then just about any approach you take to writing a program will work. You can develop some really bad habits in 1410 and 2420 because you're basically brute forcing the process. Programs are small enough to hold in your head all at one time. And you might develop habits that work just fine for small programs, but you find out that they don't scale for large programs. As programs get larger and larger, and as more and more people get involved, and their clients putting external demand, then suddenly you have to take a more principled approach to programming and to software development. So software engineering is the study of the entire process. And as we'll see later, it's more than programming is just a piece of software engineering. It's basically the art and science of managing groups of people and sets of technology and programming languages and so forth to build a product. So what we'll try to do in this class is give you experience with larger and larger programs so you can sort of fine-tune your own habits. So the way we'll study software engineering is we'll be doing C# programming in Visual Studio, which is a tool-rich environment. So one thing about software engineering is you end up using a lot of tools besides the programming language. And we'll be doing that. So how many of you have programmed in C++ and C# before? Okay. So a number of you have, but most of you haven't. The good news is C# is basically Microsoft's take on Java. At one point, Microsoft wanted to adopt Java and modify it for their purposes, and Sun Microsystems, which owned Java at the time, wouldn't allow them to do that. So they just created a language called C#. But it's basically, it's very similar to Java. And so it's not that hard to learn if you know Java. And Visual Studio is Microsoft's programming IDE, or one of them. And it contains a rich set of tools that we'll be using. Okay, so we'll be doing the programming. We'll be studying software construction tools and techniques. So you'll learn some new ideas in programming, and you'll be writing different kinds of programs you've written before, probably. We'll be learning common software architectures. So what's a software architecture? What does that mean? Yeah?
It's like an overview and outline of how the whole software will run.
Okay, he said an overview or outline of how the software will run. So that's a reasonable thing, but I have sort of a bigger picture in mind for software architecture, yeah?
How software components interact with each other and how they pass data back and forth.
Yeah, he's saying, well, how software components interact with each other. I mean, that's getting at it too. The idea is that when you write a program, if you're writing a program with a graphical user interface, there are ways to approach that problem that people before you have identified. And those are software architectures. So there are common ways to design graphical user interface programs. There are common ways to design web programs. Common ways to design apps on your phone and so forth. So those are software architectures. It's basically generally accepted ways to go about building certain kinds of programs, so that when you build something, it's not like you're building the first one. You can learn from the people that came before you. And finally, you'll get practice, as I said, working individually and working in pairs. You've had that experience in 2420, and we'll continue with it. So this next slide, which you can't see, talks about hardware and software. So what you're going to need is, you need a laptop in the class. And you're going to need a laptop running Visual Studio. And the reason you need the laptop is for the labs, because the labs don't have computers in them. There are a few loaners, if you don't have a laptop. In the labs, there are laptops you can borrow for the duration of the lab. And then outside of class, you can always work on the vast number of computers in this building or on campus. Well, probably just in this building, because you need Visual Studio. So that poses a problem for those of you that have Macs or Linux, which is probably a lot of you, because Visual Studio only runs under Windows. Yeah?
There seems to be like a Visual Studio distribution for Mac.
Well, there is a product called Visual Studio for Mac OS, but it's basically a completely different product that they just call Visual Studio for Mac. So that won't work. Yes?
Will most of the applications be like WinForm applications that we actually have to do it on Windows, or is it just like general C# development?
Well, it's general C# development, but you need to do it in Visual Studio. What you'll be handing in is a Visual Studio solution.
Okay.
And we're going to be using a lot of tools in Visual Studio, so I don't want you to be programming C# off in some other IDE. So there are various ways to get around this problem. The one that works best is to use Boot Camp to install Windows on your Mac so that you can dual boot it. You can either boot it up as running Windows or running Mac OS. And there are instructions on the Canvas webpage. There's a resources link. Click on there. There's a video that explains how to do that. It's also possible that there are these. The CADE Lab provides virtual machines, virtual Windows machines, and you can access them through your web browser. And so you're basically running Visual Studio through your web browser, in your web browser, on a virtual machine, which of course is on a real machine, sharing a real machine with a bunch of other virtual machines. But the students I've talked to have not found that satisfactory. It's very slow and clunky. Any of you know about that?
It's slow.
Yeah, they confirm that it's slow. Much better off using Boot Camp for dual boot. I've had students that refused on principle to sully their Macs with Windows. So you'll have to do something different. But, okay, I mentioned the CADE Lab. So you'll have access to all the computers upstairs in the CADE Lab, but you also have access down here in Web L130 now. So as CS or CE majors, you can get into Web L130, which is just yet more computers. And that's where we'll have our consulting hours. So the students usually bring their laptops into L130 when they want to meet with TAs. And all of you, to install Visual Studio, there's information in that resources link. You can get free, everything, you can get Windows for free if you're doing boot camp. You can get Visual Studio for free. But what you're looking for is Visual Studio 2017 Enterprise Edition. No substitute will do. But you follow directions on Canvas, you can download your own copy and install it. Yeah.
When you're downloading Visual Studio, it has a bunch of different options. Like, do you want to install these different things with it?
Oh yeah, I remember that now. That was due last time, and I forgot about it this time.
I think they can just grab the top 3 and you'll be good.
Yeah.
He says grab the top 3.
The ones that are just Windows based, so that Windows, Web, and Cloud, or like gaming.
There's like .NET stuff for C++, and
You don't need anything for C++, but you need .NET. I've got to remember to look at that and post some more information on Canvas about it. The thing is, if you choose wrong later in the semester, you'll find out there'll be some project type you'll be able to build. You can always change your mind and go grab a new. Yeah.
Yeah, if you don't select the right one, you can run the installer again and just select the ones you want. And it
Yeah.
won't reinstall the whole thing, it'll just do those like little packages.
Yeah. So it's not a do or die decision at this point. You can install or let you change your mind later. Okay. Now, there will be weekly problem sets. So they'll be due most Thursdays. So there won't be a problem set due, say, the week of the midterm or the week of spring break. Or on Thanksgiving. This is the wrong semester, so no, forget Thanksgiving. But most Thursdays will be a problem set due. Except for the first one. The first one you'll submit into Canvas. The rest we're going to submit via GitHub. So one hallmark of the class is that I very early get you started using Git and repository on GitHub to manage all your code. And the way you get code graded is we go to your repository on GitHub. It has to be one that I gave you so that I can get into it and get your code out and grade it. So at the very least, you've got to know how to get something into the repository. Is there a question back there? But for the first one, we'll just hand it into Canvas because we won't have talked about GitHub yet. There will be 12 problem sets in all. The first 6, each one involves programming. The first 6 you do solo. The last 6 you work with a partner. So you might be wanting to line up a partner for the back half of the semester. I have a late policy which says you can hand in 3 of the solo problem sets 1 day late for no penalty. So 3 of the 6, you can have an extra day. And the same goes for the pair problem sets. You can hand in 3 of them. You and your partner can hand in 3 of them late, 1 day late. You don't have to ask me, you just hand it in late. Okay? Bear in mind the reason I do this policy is so that I don't have 100 people asking me for extensions every week. So that's why I say you don't have to ask. I don't want you to ask. It's okay. Just take your 3 days. There's no bonus at the end of the semester if you didn't use your late days. So if you need them, use them. Okay, there will be a midterm and a final. So the midterm is on February 28th, which is the last Thursday of February in here. And the final is on April 28th. which is the first day of finals week. So it's like classes end on Tuesday, I think. I think the last day of classes will be a Tuesday, and then there's reading day, and then our finals. So it's coming quick this year. The way the course grades will be done is problem sets are half your course grade, 12 problem sets, and the midterm and final are half your grade. But you need to do tolerably well on both. So you need at least a 60% on both the exam average, which is 60% final, 40% midterm, and you also need at least 60% on the problem set average to get a C- or above, which is what you want. So it would be sad if you just did no assignments and made hundreds on both exams and got a D, but that's what would happen. So don't let that happen to you. Okay, have you used Piazza like last semester? You used Piazza? All right, so we'll be using Piazza. You need to get in there and get signed up with Piazza. There's a link, or a couple links from the Canvas page. And we'll use it for all communications between us and you. So first and foremost, it's a discussion forum. So you can post questions and you can answer questions. You have a
I have
question?
a question about the date of the final.
Mhm.
That is correct, April 28th?
I believe so. Is that a Thursday?
It's a Sunday.
Then it ain't correct. How did I do that?
The syllabus has the 25th listed.
Oh, okay, cool.
Okay. You know, I remember changing this for some reason. All right, now it's correct. Sorry about that. The 25th is the first Thursday of finals. Thanks for catching that. All right, I want to point something out that people don't catch with Piazza at first. It's designed to work as a wiki. So a question is asked, and there are two places to answer. There's a place for students to answer. There's a place for instructor and TAs to answer. If the student answers and they made a mistake, feel free to correct it. You don't have to post a follow-up and say, no, that's wrong, this is right. You can go in and edit the original answer. And I do that sometimes if the student posts an incorrect answer. I don't want to let an incorrect answer sit there. So rather than say, no, that's wrong, I'll just correct it. And one thing I'll do when I see an answer that I like that a student gave, I'll click the box that says that I approve. It just saves me the trouble of answering it myself. So I love it when questions get answered before I see them. So feel free to do that, but be sure you know the answer. Don't be guessing. Besides using it for that, questions and answers, I will use it for announcements. So when I want to send email to the whole class, I'm going to make a Canvas, not a Canvas, a Piazza announcement. I'll post a Piazza note. And I can override your default email settings and cause the note to be emailed to each of your accounts. So you get an email in addition to being on Piazza. Now, here's what students do, I found out. They find out that by default, they're spammed every time someone posts a Piazza. And so they turn off all email notifications. Or, yeah, what they do is they start ignoring mail from Piazza because it's just too much. They just send it to their spam bucket, which means you don't get the notes that I post. So what you want to do is go in and adjust the email settings so you get whatever minimal notifications you want about posts, which may be nothing. You may want to turn off all email notifications. You'll still get my email, no matter what you set your settings to, but it won't be lost in the noise. You can also arrange to have notification on your phone when something is posted. That's what I do because I like to know when things are posted. The worst thing to do is ignore everything from Piazza. When you want to send mail to us, don't use email, use Piazza. When you post, you can post a question or a note to the instructors, for example. Okay. You can also post anonymously. So you can try that. Okay, now, in a class like this, you're doing lots of programming. And programming doesn't have to be a solo activity, even on the solo assignments. So I encourage you to talk to each other and cooperate. And what this slide says is cooperation, do it. And then it says cheating, don't do it. So the problem is to find the difference between cooperating and cheating. So it's written in the syllabus, but let me try to spell it out. the way you can tell you're cheating, one way you can tell you're cheating is if you are basing your program on some other written solution. So if you go onto chegg.com or you go onto GitHub, you won't have any trouble finding solutions to many of my assignments. If you talk to someone that took the class last semester or last year or 2 years ago, if you want to find a solution to my assignment, you'll be able to do it. But at that point, you're cheating. You're basing, if you look at it, if you're sitting there and you got a solution here and you're working here and you're going, see, that's how they did that. Well, I'll copy that bit in. That's cheating. So when you work in groups, that's okay. But don't work on a group solution, because I don't want you to work on a group solution and you email it to everybody and then you either turn it in or rewrite it slightly. You're basing your solution on some other written solution at that point. So limit your cooperation to, how to attack the problem, or hey, could you help me with this bug, or something like that. Don't work on group solutions. So I used the same cheating policy in all my classes. Last semester in 1410, on December 26th, I sent out not one, not two, but 31 letters to students who failed the class for cheating. Okay? 31 students out of roughly 280 that finished the semester. That's over 10%. So that was kind of a bummer for me and a bigger bummer for them. But in every one of those cases, they were using a solution from a previous semester, and it was, we analyzed the submissions and it was easy to see. It wasn't like it was a closed case. So, I don't want you to cheat, but I also want you to cooperate. So if you just follow my guidelines, not basing your solution on any other written solution, you should be okay. If you have any questions about it, ask. Okay? You don't have to ask now. You can ask later. Okay, you'll notice that we're videotaping. So usually what happens is we videotape, what we do is we merge the view that you see on the screen. So we just have a wire from the laptop to that laptop there. So it's taking in whatever's on my screen, and it's also videotaping whatever it's pointed at. And then I've got some TAs there that mix it in real time. So if I'm talking like this with nothing on the screen, the camera's on me. If there's stuff on the screen, usually I'll be in a small inset on the side and you'll be able to see. So on these videos, when it's working right, you can look, you can read the code on the video that gets posted online. Unfortunately, almost nothing is working. I assume the camera's working. Is that right? So at least we got that. I can't even get anything up on the screen at the moment. But it's a nice backup. But here's the thing. You should expect it to fail from time to time, such as today. So it's hard to produce a television show from a live classroom, which is what we're trying to do. So most of the lectures will end up on YouTube. So the best thing to do is to come to class and participate actively. Ask lots of questions. And use YouTube for review or to see something that you missed or didn't catch or something like that. Okay? So I'm not giving you much chance to participate right now because I'm just talking about the syllabus. But, going forward, class works a lot better and I'm a lot happier when there's a lot of questions and answers, a lot of back and forth like we had when we were talking about software engineering. Okay? So that's the highlights of the syllabus. The syllabus is more detailed than that. But I'm happy to answer any other questions you might have about how the class is organized or what your life is going to be like. Yeah?
Are there recordings of previous semesters on YouTube?
Yes. Yeah, so there's a YouTube channel. If you search for something like University of Utah School of Computing undergraduate program, I believe, there's channels of various courses. You can find the ones from last semester. Or not last semester, last year.
How are midterms and final laid out?
How are the midterms and the finals laid out?
Yeah, are they like code-based, or is it?
So what you'll see is that for the first part of the semester, we tend to talk on Thursdays about programming language stuff, and on Tuesdays about software engineering stuff. So the final is split that way. So there'll be some questions about programming, and there'll be questions about software engineering, but there won't be large, sizable chunks of code, you're right. It's just too hard to grade. It'll be small little pieces, or read a little bit of code and tell me what it does, that sort of thing. You had a question?
Do we need to bring computers every day to class? Or?
You don't need to bring computers to class. Unless, I have some students who, I tend to do live programming in class sometimes, and some students like to follow along with that, but it's just personal taste. I will say though that I've had the experience many times of, the faculty does peer reviews of each other, so we'll go visit each other's classes and give them feedback. And I'm horrified when I sit in the back of class and see what's on the screens back there. So if you think you're good at, you're so good at multiprocessing that you can come here and watch a movie or play a game while I'm giving a lecture, you're wrong. So it'd be best if you didn't try that. Any other questions? Yes?
Were you able to work ahead in the assignments?
Work ahead on the assignments? No. You won't be able to work ahead because I'm just going to produce the requirements once a week. So, yeah.
When will assignments typically be posted?
Friday, or if I'm really on the ball on Thursday.
So we'll have one more week.
Yeah. So you basically got from Friday to Thursday to do it, unless you take a late day. Yeah.
How many hours a week do students tend to spend in 3,500?
Well, so I see some, I don't know for sure, but I read the comments people put in course evaluations. And there's always a student that says, oh, I spent 40 hours a week. Okay, that's totally unreasonable. So if it's taking you 40 hours a week, you need to rethink your approach, I think. So I really, that's a real outlier. I would say I would expect more like 10. Yeah.
They're going to be practice midterms or practice finals.
Yeah, I'll give you example, old midterms and finals to study from. And we'll do reviews and that sort of thing. Yeah.
Will TA hours and office hours be posted on the Piazza campus?
Okay, so there will be, in fact, they're posted now. So if you go to Canvas, click on Help link on the home page, you can see the schedule for office hours. So the TAs will hold their consulting hours over in Web L130 across the courtyard. And I'll hold mine in my office, which is MEB 3190A. I can tell you my hours are Monday and Wednesday from 1 to 4. But also, if I'm in my office another time with my door open, then I'm willing to be interrupted if you just want to drop by any chance that I'm there, which I often am. Yeah?
Does that mean we should expect to spend less time a week in 3,500 compared to 20 to 20?
What do you guys think?
I think most students do that, but it like depends.
Most students do spend less time in
Yeah.
35?
Depends on the project.
Yeah, they're sort of agreeing with me. What you're not doing in this class is writing reports, like you do in 25. But, wow. If that's all it took to get you to relax, I should have said that right. Your source of stress will be that you'll get these specifications of programs you're supposed to write, and it's pretty detailed and long. So you've got to be able to read and absorb and pay attention to detail, that sort of thing. Okay, any other questions? Okay, so really don't want to do this. So what we're going to do now is take a quick break. I usually take a break in the middle, and this is close enough. I'm going to see if I can get the audio-visual to cooperate. So amuse yourself for a few minutes.
Yeah, studio. Yeah, yeah. Sure.
Okay. Okay, so one thing I like to do on the first day is talk to you about where things came from.
How are babies born?
No. Well, I don't know, but this is how programming languages were born. So if you go back to the first computers were developed right at the end of World War II. Who knows why they were invented, why they were developed? Yeah.
Cryptology.
Well, there was some special purpose hardware developed for that. But general purpose computers came for a different reason. Yeah.
Was something about breaking Nazi code?
No, that's cryptography. Yeah. Go ahead.
They had to shoot wasn't it like shooting like cannons or something like that, and they had people that manually computed the.
Yeah, it was to aim weapons. So they had every new weapon that came along, every bomb, every mortar that had to be aimed, they had to create what were called firing tables for them. So it would say, okay, if you're here and they're there, and the wind is blowing this away, then you should aim it at this angle and at this declination. And it was by the end of the war, it was taking 18 months to create firing tables for new weapons. There was a backlog. The people that did the calculation, they used a combination of just people that were good at math, and they had mechanical aids that would multiply and divide and even do some numerical integrations. But it was mostly women that had been hired off college campuses, and their job title was computer. So the original computers in World War II were largely women working for defense departments, creating firing tables. What is going on? So anyway, they were trying to automate this process, and they didn't succeed until the war ended, but then they had the first computer. So assembly languages were the first way that, originally you programmed in machine language, which basically means you're writing down ones and zeros. And that became tedious pretty fast. So that's what assembly languages came away. They're like a machine-readable version of machine code. And this is not a vintage assembly language, this is a modern one. But you can see it's pretty low level. It's saying things like push-outs, or pushing something on the stack, moving something from one location to another, jumping, like jump.l3, that means jump down here, return. Very low level, cryptic, but that's how people programmed. That's the only way people programmed for maybe 10 years, in the 50s. And you take 3810, you'll be programming in assembly language. Okay, toward the end of that decade, higher level languages were being developed. So one of the first was by John Bacchus at IBM, who created Fortran. And this is sort of the original Fortran of the day. And if you look at it, how does it strike you? Does it look recognizable as a programming language? Yeah?
Sort of.
So when it says input tape, was it reading a magnetic tape?
Yeah, what it's saying there is that we're going to read from a tape, and I think it's saying we're going to use the number 5 to stand for the tape. So maybe up there where it says format 3i5, I think the 5 may refer to tape 5, I'm not sure. It's been so long. First language I programmed in was Fortran, although it was Fortran 4, and this is Fortran 1. But those ifs, for example, when it says if IA, what that means is if IA, if the variable IA is negative, you go to line 777. If it's 0, you go to line 777, and if it's positive, you go to line 701. So that was it as far as flow control. One of the big advances, the name comes from formula translation, so one of the big advances was the ability to write out expressions like this, instead of having to code something like that in assembly language. But, there are statements, there are arrays in the language. It was a language that was compiled, first one that was compiled, and people railed against it. Said this is a disaster, a bad idea. Now, can you imagine why they would say that this is a bad idea compared to assembly code? Because it was new? Well, there's some truth to that, because almost every advance in programming languages has been met with detractors. Yeah.
Because it's too slow. It's generating too much code.
Right, because it's too slow. So the argument was, no way. So think about it. This was being fed to another program, a compiler, and being translated into assembly language. And so the argument was, no way can some stupid program produce better assembly language code than a human could working directly, right? So you get better code out if your human just writes it directly instead of doing it indirectly this way. That was the argument. Okay? Good thing that argument was lost, because it's not true. And not true anymore. It may have been true briefly in the day, but nowadays you don't hear that argument made very often. Okay, another language that was invented at almost the same time. John McCarthy, who was an AI researcher first at MIT and then at Stanford, invented a language called Lisp, which for decades was the language that AI researchers used. It could not look any more different from Fortran. To a modern eye, Fortran just looks ugly. Lisp looks like what? You had to compare that to a modern language. Python. It's a little bit different. It's a lot different, but it really does have, Python has the feel of Lisp. Lisp went with, uses lots of parentheses for syntax, as opposed to the indentation that Python uses. But what that's saying is, we're defining a function called length that takes a list and returns its length. And it says, if the list is null, return 0. Otherwise, add 1 to the length of the rest of the list. So it was an interpreted language, so it's not compiled. It just runs on there's a program, a Lisp program that you run it in. You don't declare any types, it's dynamically typed. So you see that in Python. It's based on lists. In fact, the name comes from list processing. It was the first language to use the kinds of memory allocation that we take for granted now in C# and Java and so forth, where we have, when you create things, we allocate memory, it's allocated on a heap that was garbage collected. Deallocated stuff is automatically, things you don't need anymore is automatically found and deallocated. So it was way ahead of its time, I think. So then in a committee of computer scientists, half from Europe and half from the US, got together in 1959 and 1960 and created a language called Algol 60. And you can think of Algol 60 as being the precursor of a lot of language that we use today. So it was block structured, meaning that you have begin and end. Nowadays we use braces for that. It had familiar control structures, like you see for loops there. Assignments, the colon equals is assignment. It had arrays and records, which were sort of like objects in a sense, not really the way you think about them today. And you had declared types, so you up there were declaring P and Q to be integers. So it looks different from Java, but you can definitely see how Java might have its roots in something like this. In 1967, a language called Simula. Now, first of all, I don't want to imply that these are all the languages there were. through the 60s, the 70s, the 80s, even today, lots and lots of languages are invented by researchers to try to investigate new ideas, and that was true then. I remember in grad school reading a paper, the title was The Next 700 Programming Languages. So it was about changes the author thought we would see in the next 700 programming languages. I'm showing you the influential ones. And what Simula added was classes, objects, and inheritance. So it built on top of Volleyball 60, and really is the first object-oriented language. But it took the garbage collection idea from Lisp. It took the base syntax from Volleyball 60 and added in classes, objects, and inheritance. 1967. 1972, Dennis Ritchie at AT&T Labs invented C. So there's some original C up there. It had a very terse syntax, which is pretty much familiar nowadays. It gave you low-level access to machine resources, so it's a low-level programming language. It's sort of, nowadays people view it as sort of the assembly language for today, sort of a very low-level language. It really didn't do much in the way of type checking. And it had pointers. You could address places in memory. You could compute addresses in memory and use them. So that was C. C was invented sort of as a language to implement an operating system called Unix, which eventually evolved into Linux. And this was all done at AT&T Labs, Bell Labs. And it's hard to explain nowadays what that means, but back in the day, there was only one phone company. That was AT&T. And I remember you really couldn't buy a phone. I mean, you rented them from AT&T. It was a very different world back then. So they were a huge thing, and their researchers developed a hugely influential language in the form of C. Strostrup in 1979 came out with C++. He basically added classes to C. He layered object-oriented programming on top of C++. So you can think of, he got these ideas from Simula, and he tried to make, he tried to make the language safer, so there's a sort of a safe way to access memory. But still, in C and C++, if you want to, you can completely subvert the type system and access pieces of memory that you weren't, that you probably shouldn't be accessing. Still pretty low level. Okay, Java came along in 1995. It was originally designed to program small things that would be connected to the web. Like nowadays, we didn't back in the day, but nowadays we have like smart refrigerators and smart televisions. And so the thought was these things would be interconnected someday, and Java was going to be the language that ran on them. But about the time they invented it, the World Wide Web came along. The web came along in the early 90s as well. And Java quickly became the language of the web for a while. It was used to write programs that ran on web pages. And it borrowed a lot. It takes the syntax, obviously, from C and C++. Inheritance comes from Simula, another language called Smalltalk. It's got the Lisp memory model. In fact, one of the main developers of Java was an old Lisp programmer. Just from his point of view, I think he just dressed up Lisp in different syntax and now gets people to use it. And it has this idea of platform independence. Compile once and run everywhere. And that's what C# uses, and that was controversial as well. Again, people said that'd be too slow. And in fact, Java's a little slower than C++. But what happens is, as languages advance, we're taking things that people used to have to worry about and letting the language worry about them instead. And that makes people more productive. Used to be, computers were incredibly expensive. Computer time was incredibly, was really expensive compared to the salaries you would pay people to program computers. And so the valuable commodity was computer time. Now, of course, it's the opposite. Computers are all but free, and it's the programmers that cost a lot. And so you see the design of the tools reflects that. We want to make people efficient. C#, as I mentioned, was Microsoft's take on Java. So it came on in 2002. And as you'll see, it looks a lot like Java. And Python's actually older than Java, although Python goes through versions, radically different versions. So anyway, that's where things came from. Now, we're going to talk about software engineering. Okay, so this is from a classic software engineering text, in which I had to modify by adding that yellow box over there. But this is sort of I just showed you how programming languages evolved over time. Let's look and see how software has evolved over time. So in the early years, these red years over here, what we had were batch systems. Software was custom, it wasn't widely shared. It was just, software was specific to a local installation. But what is a batch system? Who knows what that means? Yeah.
A whole bunch of punch cards, you put them in order to a computer, and you run them one by one.
Well, he said, he was mentioning punch cards, and yeah, punch cards were used. Let me tell you a typical way you might interact, because actually I had a job in 1975 when I was a freshman in college, interacting with a batch system. So I had a professor I worked for, and he would want to run a program he had that analyzed trace elements in the ocean water. And so he would design it, he would create a data set. And I would take his data and I would go punch it on the card. So I'd go to a card punch machine, and each line of input was a card. So I would punch his data on the cards. And then you take the cards and you submit them to someone at a counter. So the computers were back behind the counter. And people at the counter had sort of white lab coats on, blue lab coats. So you'd hand them the cards you wanted to use, and they would run the cards through a card reader, and it would maybe produce output on the tape. And then the operator would then take the tape and mount it on a tape reader, and then it would read the data in the computer, and eventually the output would be created. It would print out on a line printer with fan-fold pages about, I don't know, about this big, that were folded up. And then, 15 minutes after you submitted, they would hand you the stack of output, which I'd run across the street to the professor. So that's a batch operating system. So what makes it batch is the human component. The humans were you got the card reader separate from the tape reader, separate from the processor, separate from the printer or whatever, and people shuttling around, moving data from one place to another. And their job, I think I used the word, they were called operators. And when they were replaced, what were they replaced by? Operating systems. So in the 60s, people had the idea to let software replace these people that are doing this job. I'm not sure why this persisted into the 70s, but I did have that sort of that tail end experience with it. So that's what it was like during this era. And I remember taking a field trip to see a computer. Okay. Second era is more like the late 60s into the early 80s. So that's when there were operating systems and there were computers, but the computers were still kind of remote things that you access via terminal, and typically many people using the computer at the same time, using time sharing. So operating systems were developed for that. Databases started to appear and software started to be a product. It was still very much the computers were right behind the counter. Regular people didn't touch computers. You really often see them. You accessed them through a terminal that had like 80 columns and 24 lines of characters on it. That was your interface. If you've ever used a command shell window on a Mac or in Windows, just imagine that as your only way. You've just got that. You've got a hardware version of that window. And that's how you interact with a computer. So the blue era in the 1980s started to be distributed systems. So multiple computers that talk to each other, that were networked. So that the internet has its roots in the 70s and 80s. computers started to get cheaper, and it started to have, computers started to have a consumer impact because personal computers started to appear. And then the fourth era, sort of into the beginning of the century, basically governed by the internet. So people started to have powerful computers at home. Object-oriented programming became the way to program, a predominant way to program, and the internet appeared. And then the web appeared. Who knows when the internet started? Yeah?
99?
No, long before 99. Yeah?
The early 90s?
The early 90s is when the web started. When there first were web browsers and HTTP web addresses. Yeah?
Was it 1974?
It's more like 1970, I think. I may be off by a year. It started as a project by the Defense Department to see what they want to do. They funded research projects around the country at universities. They wanted to see what would happen if they linked the computers at these research sites into a network. So they created what was called the ARPANET. ARPA stands for Advanced Research Project Administration of the Defense Department. And the first 4 sites on the ARPANET were 3 in California and 1 here. We were number 4. So University of Utah was number 4, the 4th node on what became the internet. Okay, so I use these slides. I've taught this class for a long time, and I finally realized I needed to add this yellow box. What do you suppose? So that's today. What's different about today? Phones. Cloud computing, mobile computing. Multi-core processors. So we've gone all through these eras, so the demands on software have changed radically from the old days. And it's always been a race to keep up. Hardware changes pretty quickly, and people developing software are struggling to keep up and stay current and figure out ways to deal with the new demands. And for that entire time, people have been talking about the software crisis. So we're 60 years into the software crisis. Computers are pervasive, they're everywhere. That becomes truer every day. It's important they be reliable for a number of reasons, not least security and privacy. And yet, and major damage can be possible when they fail. Programs have literally killed people. Faulty software in medical devices has killed people. And there are other lesser kinds of failures that happen all the time. As I was mentioning, it's hard. Software developers are hard-pressed to keep up with hardware development. And it's just a struggle to build software fast enough and reliably enough. Many projects are started and then abandoned. So it's tough. It's a hard business. There are lots of tools nowadays, but still, it's hard. Yeah?
Is one of the problems just that there isn't enough software developers?
I don't know if it's not enough software developers. It's that, it's easy to take a programming language and start writing a program. But what's harder is to get one that's correct. I mean, think about what you tolerate in software. I mean, you get software, and it's no big deal if there's a bug in it, right? And it gets fixed in the next release. You live with it. You sort of expect it. But you don't expect that sort of thing with other kinds of products. So it's tough. There are just too many degrees of freedom in software. So a lot of software engineering is figuring out ways to basically tie programmers' hands, right? So that they, instead of doing anything they can think of, they sort of focus them on a good way to produce code. All right, as I mentioned at the outset, techniques that work for small programs don't scale. So if you're writing a program for 1410 or 2420 and you write it this week, what do you do with it next week? Yeah, you forget about it. You throw it away and you go work on next week's program. You don't have to live with your mistakes. So in this course, there'll be 2 major projects. The first one, as I'm sure you know, you'll be building a spreadsheet. And it'll take 6 assignments to do it. And what you'll find is that, okay, the first assignment, not too bad. You got your thing working. Then you go to the next piece. The first two pieces are independent, so that's fine. Third piece, you've got to integrate these other pieces. You start having to put them together and modifying your old code, and you start to feel a little bit overwhelmed. You can start to feel overwhelmed because maybe you forgot how the code worked that you wrote 2 weeks ago. You didn't put any comments in. And now you look at it, it's like someone else wrote it. Yeah?
Do we get to use any framework that is provided, for these assignments, the 6 assignments?
Yeah, I mean, I'm sort of, especially for the first series of assignments, I serve as a designer and give you a framework to work with. But anyway, you'll get at least some experience of what it's like to live with code over a period of time. Now, what you don't have to do, this would be interesting, if a year after you take 3500, you had to take another class, and what we did was we gave you your old code and asked you to work on it again. All right? That would be a shock to the system. But at least you got to work with it for half the semester. And what you find is you may have to adjust your approach to programming. Maybe you never saw the need for comments before, because maybe they're not very important if you're going to throw the code away after a week. But if you're going to keep working on it, you start to appreciate the need for comments and good variable names, and for doing good version control so you can keep track of different versions. And when you break your code, maybe you'd like to be able to go back to a version that worked, but oh, you didn't save it. So those are the kinds of things we look at in this class. Big systems live on beyond their original developers. So you end up working with code someone else wrote. It says here, a majority of the efforts on programming is expended after the initial release. So it's not like it's over when you release it, it's just starting. Things can change, requirements, expectations can change. Part of the problem is software is easy to modify. If you're not careful, you modify it and break it. Now, this is how hardware fails. So let's say you buy a car, or you buy some sort of device. So some number of them, so time passes, some number just have, cars with lemons or whatever, it was made wrong. But if it works at all, it's going to keep working, and then eventually it's going to wear out. So that's sort of how we expect hardware things to do. Keep them for a while, and then they wear out. Now, you might think that's what it would look like for software. And it's sort of a different comparison. But in this case, what it means is software starts out a little bit buggy, but then it gets fixed, and it just gets better and better with time. It doesn't wear out. It doesn't wear out in the conventional sense. Is that your experience with software? How would you draw a curve?
Really, really spiky.
Okay, so I got people drawing spikes. I mean, it'd be nice if the world were like that. Yeah?
Almost like a bell curve.
You said almost like a bell curve? Well, this is what Pressman thinks. So there's the idealized thing. You get the software, it has some bugs, they get ironed out, and then it just works great, and then it becomes obsolete, and you get something new. But he says that's what really happens. So look at the blue line. You get, it starts out like we saw. The first release is made, and gradually bugs are taken out. And then there's another release. Suddenly there's more bugs. And then they gradually get taken out, and another another release. But notice the overall shape of that blue line. It becomes worse, not better with time. So if you're not careful, you end up looking like that blue line. It'd be nice if we could produce software that looks like that red line. Okay, so I've said a lot about software engineering. And this picture here sort of attempts to show you what software engineering is. The production of software is a human-centered enterprise. So essentially, you're managing, if you're in charge of a software engineering project, you're managing people, you're managing hardware, you're managing customers. And so software engineering involves computer science, certainly. It involves management and sociology, because you're managing people. People are working together. It involves knowing about systems. It involves knowing about psychology and human-computer interactions. So it's a big block. It's a lot less tidy than just knowing how to program. more than just programming and algorithms. Now, there's this thing called the software lifecycle, and we will, you'll spend some time in this lifecycle, and it has phases, and the phases are typically called something like analysis, where you figure out what you want to build. Then there's design, which is, okay, given that we need to build this, how should the program be organized? Then there's coding, which you're most familiar with, and testing, make sure it works. Obviously, mistakes are easy to correct the earlier you find them. So if you make a mistake in the analysis and you don't realize it until you've written the program, that's an expensive mistake to correct, right? You wrote the wrong program in that case. And then after testing, you go into maintenance. And that can consume a tremendous amount of time. Now, traditionally, there was what was called the waterfall process. So in the waterfall process, what people did was, if I go back to this, they did all the analysis. So they wanted some spanking new complicated program. So they would just sit and spend months and months and months figuring out what it was they wanted to build. And they would write reports, and generate documents, and have meetings, and get people to sign off on it. And once they had it all figured out, they would go design. They would have some people that would design, okay, what classes do we need? What methods do we need? And then once that was done, again, that could take months, a year or whatever, then the programmers would start implementing the design. And then when that was all done, it would be tested and corrected. So that was a traditional waterfall process, but it's fallen, it's really not done that way anymore. Nowadays, you read a lot about agile, hear a lot about agile processes. The idea here is you still follow the same thing. You've got to figure out what you're going to build and how you're going to build it, and you've got to build it and test it. But instead of doing this over a period of 6 months for each step, it happens over a period of, the whole process happens in a week or two. So you don't design the whole system. You just get started with something. You build it, test it, show it to your customer. That looks good, let's add this. Cycle again. So you're every 2 weeks, you've got a growing program that works, does something, and you gradually figure out what it's going to be. So that here, rather than taking many months and getting things right the first time, here it's more like change your mind a lot, get a lot of feedback, talk to people. Yeah.
I'm really risk of this becoming like a Frankenstein's monster, where you're just replacing kidneys and lungs and whatever.
Yeah, I mean, yeah, there is that risk. But I think what was found is that people just weren't very good at the outset of following the waterfall method and getting it, investing all this time to get it right and then not getting it right. The agile process is just an admission that, we gotta chip away. We can't think of everything, so we just get something working and add to it. Okay, now, that's sort of been a high-level introduction to object-oriented programming. Now I want to tell you in a little more detail what we're going to be talking about here, what we'll be learning in the class. So as I mentioned, we'll do C# programming on Visual Studio 2017 Enterprise. We're going to use a lot of tools. For example, we use version control, Git. And I mentioned I'll force you to use Git because that's how you get your programs graded. But it's really, really good skill to have. To be able to use Git in particular, use a version control system. We'll talk about that in more detail next week. We'll emphasize testing a lot. So you need to thoroughly test your code, and it's not uncommon for students to write their assignment and submit it thinking it's correct and fail 40 of the 50 test cases because there's just something they didn't understand, something that they got wrong. And we have a process of, once you see that you misunderstood something, there's a way to correct the mistakes and get it regraded. But it's an eye-opening experience when your code is assessed by the hard, cold reality of a test case. So you'll need to get good at writing test cases. You'll need to get good at using debuggers. The debugger in Visual Studio is really rich, and it has lots of features. So it's good to be familiar with that and learn how to debug effectively. We'll use tools in Visual Studio to build graphical user interfaces. We'll use a profile in Visual Studio, which shows you in a slow-running program where is the time being spent. We'll talk about modeling tools for visualizing programs and issue trackers for keeping track of what you need to do. There are probably some that I left off here. So try to make use of a lot of tools. There'll be standards for documenting your programs. There'll be standards, about how programs should be organized and how and coding style to use. We'll learn about design patterns. So these are all techniques for writing programs, for designing programs. We'll learn about database design. We'll write programs that use databases. We'll learn about code reviews. Probably ought to do some in lab sometime. You'll learn some new programming techniques, possibly. Iteration abstraction, properties, delegates, lambda expressions. Those are aspects of C# that you don't see necessarily in Java. Database programming, network programming with sockets, multi-threaded programming, where you're using multiple cores at the same time. Constructing graphical user interfaces. So sort of some new programming ideas that might be new to you. We mentioned software architectures. You're going to look at, we'll start, your first assignment involved what's sort of an antique architecture called pipe and filter. I'll say more about that later. You're very familiar by now with object-oriented designs. We'll look at client-server design. We'll look at event-driven programming. We'll look at model view controller. And we'll look at RESTful APIs. So we'll look at a variety of different ways to organize programs. And I could add database-oriented programs on there as well. So that's, in very broad strokes, what we'll be talking about. Now, I want to finish with one more topic. And that's coding standards. So who knows what is a coding standard? A standard for coding.
Documentation to cover how the code should be written.
Say again?
Documentation written to cover how the code should be written.
Okay, so yeah, it's a lot of companies, you go to work for them and they have a way they want their code to look. They may tell you how it should be indented or whether the first letter of a method name should be capitalized. And it can sound kind of silly, but why would a company have a coding standard? Yeah?
To make it easier to read and maintain.
Right. Make it easier for other people to read your code, or you to read other people's code. Have you had the experience of looking at someone else's code where they weren't indenting their code the way you do? And it looks kind of weird, and it's kind of hard to get your head around it. So people working together, if they got some sort of common style, it just makes it easier to get into other people's code and understand what's going on. Now, I'm not going to impose any kind of coding standard, but I do expect you, there is sort of an expected style in C#. Visual Studio provides a default indentation style, and I expect you to use that. It's really easy to use, it just does it for you. You'll notice that some of the expectations are different than they are in Java. So for example, in Java, method names always start with lowercase letter. In C#, the style is to have method names start with an uppercase letter. So just emulate the code examples I give you and the examples you see online of C#. And then we will have a common style. But I just wanted to show you, I have some excerpts from Google's style guide for Java. So this would be things that they give their engineers. They say wildcard imports are not used. And what's a wildcard import? Yeah?
Asterisks.
Right, you say import java.math.star. Okay, so for whatever reason, they don't want that. They want the dependencies to be explicit. It says each class orders its members in some logical order which the maintainer could explain if asked. So they stop short of saying, okay, first I want the instance variables, and then the constructors, and then the public methods, and then the private ones. But they want you to have some, not just to be willy-nilly, but there's some logical reason that you put things the way you did. Always use braces, they say at Google. You know, if something, do one thing, one statement. A lot of us just say if something, and then give the statement. Google says, put that one statement in braces. Okay? If it's good enough for Google, it's good enough for us, I think. So I've tried to develop the habit of doing that. Don't put two statements on one line. Think about if your statement doesn't fit on a single line, think about where you're breaking it. I mean, look at how many words they do here. What this basically says is, make it obvious how operators are grouped. So if you say 2 times x plus 7, which operation is done first? Does it do 2 times x and then add 7, or does it multiply x plus 7 by 2? Yeah, most of us know that it does the multiplication before additions. But there are lots of operators in programming language besides multiplication and addition. And there are all these precedent rules that spell out, if you don't use parentheses to group operations in what order they're done, Google says, don't expect people reading your program to know that. Unless it's completely obvious, give the parentheses, use explicit parentheses. Now, this is just stuff they've learned through hard experience. Look at this one. So, I don't know if you can visualize this, but imagine you declaring a bunch of instance variables. So you say private x variable name, private type variable name, private some other type variable name. And some people like to maybe have a comment after each one. And so some people want maybe all the variable names to end at the same column. So they put in spaces to justify them. Or they want, no matter where the semicolon is, they want the comments to line up. So they put spaces in between the semicolon and the slash slash. This is saying, don't do that. And why is that? Why do they say don't do that? Putting white space in to format things. Yeah?
Depending on how it got loaded on another program, when you're reading it, maybe that white space looks like it should have been an actual line
that's true.
break or.
Yeah, I've had, especially if you're using tabs instead of spaces, the white space can get corrupted, yeah.
This doesn't really apply to Java, but it does apply to other programming languages. That some programming languages, you actually use the white space over the tabs.
Well, that's true for Python. Yeah. But we're not talking about indentation here. We're talking about lining up comments maybe, or lining up the variable names that, like if it says private static variable or private non-static variable, we still want the variable names to line up when you add white space. What it's saying up there is that it's too easy to break. It's too hard to maintain. It's a pain to declare a new variable because you've got to add white space to make things line up. So they don't want you to do that, or at least don't complain if someone breaks it.
You skipped the second paragraph on that one.
Yeah, well, I'm sort of hitting the highlights. I'm not proposing this for our style guidelines. I want to show you that the style guidelines exist, because you won't be surprised when you get a job and you need to look at style guidelines. This is just saying to put a break or continue, return, or an exception at the end of each piece of it. Don't let control flow through unless you mark it with a comment. It's talking about how to capitalize class names and method names and constants. When to use annotations, saying think twice before you override object.finalize, which I'm certain I've never done. I like this one, talking about finalizers. Who knows what a finalizer is in Java? Yeah, okay. So what they're saying is if you're tempted to override it, don't do it. And if you absolutely must, read and understand effective Java item 7, and then don't do it. So I guess we're ahead of the game. There's one here. This whole paragraph is saying, when you write JavaDoc, it's saying the first sentence, if you will, isn't really a complete sentence. It's supposed to be a sentence fragment. So you don't say this method returns thus and such, or something declarative like save the method, or save the record. Your comment says something like, let's say it's a method, returns the square root. Right? That's not a sentence. You don't say this method returns the square root, computes the square root. What they want you to say is returns the square root, and then add more. So they're picky. And the reasons, this last slide here talks about, we've talked about why you have coding conventions. And you can see Microsoft says, is to standardize the style so that you and others can easily read. Sun/Oracle says your code is a product and it should be as carefully engineered as anything else. Richard Stallman from the Free Software Foundation says the purpose is to make the system clean, consistent, easy to install. People learn that certain syntax is error prone. So that's